Коллеги, добрый день. Я рад, у нас сегодня начинается первая лекция из серии лекций, которые нам представляет Imperial College London. Алessandro Astolfi прочитает лекцию по робототехнике. Я передаю слово без лишних представлений, потому что вы уже успели прочитать анонс, который я вам рисовал. So, Alessandro, please.
Thank you very much. So can you hear me? All right. So, well, it is a real pleasure to give a lecture here. And of course, this is my first time in Moscow, and I was definitely impressed by everything I've seen. Very little, but everything that I've seen. So, okay, the talk of today is on robotics and autonomous vehicle, and it is essentially an high-level talk in which we discuss what robots can do for us, what autonomous vehicles can do for us. I mean, in the sort of traditional way of thinking, a robot is an object, a mechanical object that moves. An autonomous vehicle is something that flies. Now, today, this is completely out of date. I mean, it's very easy to make things moving and so on. What we want them to achieve specific tasks. They have to interact with the environment, they have to interact with each other, they have to communicate. And first of all, they have to interact with a human being. Okay, so, I mean, robotics, as I was taught when I was a student, and robotics today are two completely different disciplines. I mean, in my days, the issue was how to control a manipulator, something that picks this glass and put it there. And these days, we would like to have something which is, you know, not really the Star Wars type of droids that do whatever we want, but, you know, along these lines. And, you know, if you look at nowadays technology and you watch a few science fiction movie of 20 years ago, you see that actually, you know, we are going in that direction. I mean, the gap is not so, you know, between fictions and what we can achieve is actually not that large. Okay, so most of this talk will be based on my research activity, personal research activity, which means that, you know, despite the high level approach of the talk, then if you want to know the details and if you want to know how we develop some of these results, I'm be really happy to discuss all this with you. Well, of course, if I can fix the microphone first. Okay, now, the picture on the right is a very famous clock. This is the longitude clock of Harrison. And Harrison was not really an engineer. I mean, it was a very skilled person, a very ingenious person. And he was able to devise a clock that would keep the time as you cross from London to Barbados, despite the waves, despite the disturbances, despite variations of temperature and so on. And this, for the time of Harrison, was really an achievement. So he made a mistake of 5 seconds as you travel from London to Barbados. And this is probably one of the first jewels in terms of mechanical system where you can really think that this is a robot because there's a lot of mechanical parts that interconnect to each other. There's a lot of disturbances. There's a lot of interaction with the environment, but still you achieve a goal. Okay, so this is probably a robot long before we were even thinking about robots. Now, the way the talk is organized is in several layers. Okay, so we will be discussing small objects, and we will see that this is a type of probe that you can insert inside your body and you can use for surgery. And of course, it's very difficult to make such a tiny robot that will achieve a task, will not destroy anything, and will navigate throughout the body of a person, for example, from one leg all the way to the heart. Okay, and if you think that you can do this not on young people like all of us, let's say, but on elderly people, then this may be extremely difficult, okay? Because it is very difficult to navigate this object inside the human body. You see now that the notion of navigation, which is what I was taught a long time ago, that, you know, you want a robot to go from here to there and there are a few chairs in between. I mean, this is really a simple task. I mean, here you would like to have a tiny little object go in an environment that you don't know precisely and without causing any damage. And you want to have a precision of, you know, 1/4 of a millimeter, even less than that. On the other side, there is a large object, not very large. I mean, this is an unmanned autonomous vehicle developed by British Aerospace. And this is mostly for surveillance. And so there are some commonalities between these two objects, despite the different type of size and the different types of applications that they have. Now, the next level is where these objects are applied. So we want to go from C underwater vehicle to ground vehicles, so typical mobile robots. And again, we will see that mobile robots can do a lot of things for us. And air robots. I mean, this is a very strange object. I mean, this is a type of wind turbine, and this is generating electricity. But unlike wind turbines that are not very good for the landscape, and that, you know, once you have installed them in a place, you cannot really move them. I mean, even if they are offshore farms, it's extremely difficult to maintain this type of object. These wind turbines are like kites, okay? So you can simply fly them and generate electricity. Now, it looks like a long way, but actually it's not a long way. There's some experimental devices that are already producing electricity. Now, if for whatever reason the environment changed, that you don't have wind anymore in a special area, you can simply roll the wire and deploy this in another position. Now, the next layer is autonomous vehicle. So this is like a toy helicopter that is supposed to fly in a special reason, and cooperative object. Cooperation is extremely important these days. I mean, you know, there's a lot about so-called agents, which means large groups of systems which are essentially a copy of each other. So each single agent is a copy of each other, but they have to work all together. So this is an image of a telescope, and this telescope is a very wide telescope. Actually, you cannot even see a human being, but it's approximately of this size. Now, what you want to do, you want to devise a mirror, and the mirror for this telescope is extremely difficult and expensive to construct. So what you do, you build thousands of tiny mirrors this size, and then you put all of them together. So from a construction point of view, you save a lot of money. You save a lot of effort, because making a very small mirror in a high precision is very simple. To make a huge mirror is almost impossible. But then you have a problem, because you have to make sure that all the edges of this mirror are properly aligned if you want to have a good picture. And for example, if you want to have a flat mirror, you're not really measuring, you know, the distance of each one of the mirrors from the floor, because you would like to have a precision of the micrometer. So what you really measure, you measure relative displacement of this mirror. So you can measure that there is a small displacement between these two mirrors, which is a couple of micrometer, and then you want to adjust. But as you adjust on one side, then you make an error on the other side, and so you adjust on the other side, and so on. So you have a very large scale, thousands of similar objects that you are trying to use all together to achieve a goal. Okay, so this is extremely important. Cooperation versus autonomous is extremely important these days, because it allows to sort of have a lot of different objects that you could use for a unique goal. Okay, now, what are the objectives and the motivations and the methods for this presentation? So the idea is that we would like to use systematic tools, and most of them have their roots in math, in differential equations, in theory of dynamical system. And engineering intuition is always important to make a step at some point. So you have a lot of theory, but then at some point you would like to build something, you would like to develop a product. So there is a point where you have to stop with your systematic tools, and you have to use engineering intuition. And we want to have this to develop new ideas, new applications, and possibly products at some later stages. Now, it is extremely important in order to achieve this goal to be able to have knowledge transfer across disciplines. I was trained as a control engineer, and as a control engineer, you just have a control loop that you have to design. Someone is thinking about the model, someone is thinking about the actuator, someone is thinking about the sensor. This is not true anymore. If you want to develop new ideas, new products, new applications, you have to have a system view of everything. You have to be able to understand interaction between fluid mechanics, electronics, control, communication, signal processing, expert system, the way human and machine interact. You have to understand that topology and performance are strongly related. If you go back to the example of the mirror, then you have a topological structure, because you can think of all the way the center of masses of the mirror are connected. So you have a graph, and this graph, on top of it, may have a communication graph that may be different from the graph that is constructed between the various mirrors. So what happens is that each mirror is communicated, for example, to only the neighborhood mirrors, whereas they may be mechanically connected in a different ways. So the topology, there is a communication topology, there is a structural topology, there may be a control topology, because you may want to close loops in a different way. And topology and performance are strongly related. It would be nice to be able to communicate to all. Okay, each mirror communicates to all the others, but this may be too expensive, it may be too slow. Okay, so once you fix a topology for communication, for control, then you restrict performance. And there is a very nice interplay between the two. And finally, we have to understand that cooperation and autonomy, again, they are at the opposite side of the spectrum, but it's important to understand that you may have autonomous vehicles which are cooperating all together in order to achieve a common goal. And we will see that the way we formulate cooperative goals for autonomous vehicles is extremely important, because there is a cooperation in space, there is a cooperation in time, there is cooperation in space and time. And it is extremely important to understand what type of problems and how to achieve this. Okay? All right, now all these, unlike robotics and autonomous vehicles as they used to be regarded like 20 years ago, they have to improve efficiency, reliability, availability, the value in what we can say scientific discovery, health and safety, so human well-being, production of energy and the way we distribute energy, smart buildings, transportation system, medical practice, and so on. So robotics these days actually has large impacts on the way we live. And whenever I say the word robotics, again, I mean a mechanical system with electrical part, with an interaction with the environment, so a much more complex object than what used to be a robot 20 years ago. Okay, now the talk is essentially based on case studies, and mostly from an academic perspective. I'm an academic, and partly on personal research activity. So I've actually contributed to the development of some of the applications that we're going to see. So we are going to discuss robot manipulators, mobile robots, underwater robots, autonomous vehicles, and then at the end we're going to discuss cooperative systems. So we could say that the first four objects are somewhat autonomous systems. Then we're going to have a look at the sort of abstract way of defining a cooperative system. And then we are going to look at a new application which is called dynamic sets. So, to give you an initial idea of what a dynamic set is, think of the clouds. Okay, so the clouds are moving in the space, and the way we see the clouds, I mean, these are essentially sets moving. And it looks like this is very far-fetched, but we'll come back to these clouds later on. Okay, now you would like to understand the way clouds behave, for example. But, we don't have to be clouds. They may be flock of birds. They may be objects. You may have an oil spill in the ocean, and you want to understand the way it behaves. You may want to understand the way a bushfire, which is another set, behaves. Okay, so this is a type of way of looking at autonomous system, because most of these systems are autonomous, but we would like to understand the way they behave. Okay, now robotics, robotic manipulators. So this is the simplest possible class of robots. But while robots are used to be considered like, simple robots that can be used in pick-and-place operation, nowadays robots can be used for much more interesting and much more useful applications. Now, suppose that you have a patient that has suffered a stroke, for example, and has to undergo rehabilitation. Now, what happens typically? You have the patient, he has to go to some place, have rehabilitation, and come back. It has actually been shown that the time and effort that the patient has to take to go to a rehabilitation and come back, most of the time is such that the positive effect of the rehabilitation is almost zero. For example, if you have a problem to your back, you drive 1 hour, you go there, you have physiotherapy, you go back home for another hour driving, and so, you wasted your time because, all the time that you have been in your car driving has been bad for your back despite the rehabilitation. So we want to devise now a little tiny object that you go to your doctor, the doctor will give you take it home, like, the coffee machine. In the morning you wake up, you have your coffee and you have your rehabilitation. Okay? So this is a type of rehabilitation, which is a very simple robot, where you can put your hand, and this robot will initially move your hand. So, for example, if you have some problem and you need to start again moving your hand because of an accident and so on, so the robot will initially move your hand, and then will sense the force that is applied by your hand to the robot, and eventually what happens, you will move the robot. Okay? So there is an interaction very clear between the robot and the environment. The robot will initially be driving your hand because you have no force on your hand, and as you progress with your rehabilitation, then you will be able to drive back the robot. And the robot will be devised in such a way that you can repeat an experiment several times, and in this way you sort of have your rehabilitation at home or wherever you want, in the office, for example, and you don't lose the good effect of this rehabilitation. So this is the simplest possible example that I can think of a very simple mechanical system. You see, this is actually very simply built, that actually requires a very sophisticated interaction with the environment. You have to be extremely gentle at the beginning if you want to have some success in the rehabilitation, and on the other hand, you want to be able to measure the progresses that you are doing your rehabilitation. Okay, now how do you abstract this? Well, this is what a robot used to be. I mean, you know, when I was studying robotics, I was given this type of pictures. So this is a mechanical system, is a multi-body mechanical system that we can describe via differential equations. Now, these are classical differential equations of second order type, where Q is essentially the position of all the links, Q dot are generalized velocities, and then we have the inertia matrix, the centrifugal terms, the effect of gravity in G, and the external forces. And now there is an additional ingredient, which is the interaction with the environment. The interaction with the environment typically is given in terms of a set of constraints. So you cannot you can touch this table, but you cannot go underneath the table. You can go at some speed, but not all speeds are allowed. And so you have a certain number of constraints which are sort of specifying the type of interaction that you have with the environment. Now, if you want to be able to apply a force in some point, for example, as you touch a table, if you want to draw on the table, you should be able to touch it, to apply a force, but this force should not be too much, otherwise you break your pencil, for example. Okay, so there are external forces, so Fe are all the external forces, and you can divide these forces into forces which are sort of the control forces and forces which are given by the user. Okay, so in the case of the robot that we have seen before, there may be control loop which are generating forces, and there may be forces which are generated by the user. If you have a mobile robot approaching you and you want to push it away, you want to be stronger than the mobile robot if this is a domestic robot, because you have to be able to avoid that, for example, you have an accident. Okay? Now, the task of the robot is typically expressed in terms of a desired position or force for the end effector, which is, in this case, the tip of the robot. In the previous case, you get desired position, velocities, and trajectory and forces for this part here. Okay? So you want to be able to feel that there is a force applied to the robot, and the robot will apply a force back, and you want to be able to move this part in a very specific way. For example, you may want to have rotation orthogonal to the plane. So this is the way you formulate the problem. And now, there are all sorts of type of robots. I mean, this is a robot, okay? It's a toy that you can buy for kids, and, you know, it has a lot of additional objects. For example, you know, it has sensing devices, it will understand if you stroke it, and so on. But at the end of the day, it's a robot. I mean, it's composed by little robotics arm, like the one that we had before. There are 4 for the legs, 1 here, and we can consider another there. And there is a lot of interaction, tactile interaction with the environment, and even visual interaction with the environment. Now, robot control is now a well-understood discipline. I mean, you can control a mechanical device to make sure that it does what you want in several different ways. So what happens is that you have your robot, which is a dynamical model of your robot. You may have uncertainties, which are represented in this delta block. And then you have disturbances, which are external disturbances that you don't model. It is always important, whenever you do dynamical system theory and this type of things, to distinguish between disturbances that you model, represented by block delta, and disturbances that you don't model, disturbances that can affect your system, but upon which you don't have any specific information. And then you have a task, Z, which this is the actual task, and ZD is the desired task. And then typically you would implement one loop, a feedback loop, which is processing available information, available measurement on your robot, and is generating a control signal. But then you also have a feed-forward controller. The feed-forward controller essentially will tell the robot what to do in the case that the big delta and the D are identically equal to 0. So if the robot is on the right track, then there's no need for feedback. Feedback is only to adjust performance as you go along. So the goal of the controller is essentially to drive to 0 the difference between Z and ZD. Okay, so this is a very simple problem from a mathematical point of view that we can formulate in a very clean and neat way. There are two important issues here. Okay, first of all, we should be able to solve this problem, but for robots, which are reasonably gentle dynamical systems, it's easy to solve this type of problem. What is actually extremely important is to understand what ZD should be. What is the desired behavior of your robot? It's not only pick and place or move from here to there. The robot should do a lot of other things, should be able to communicate, should be able to avoid obstacles, should be able to interact with the environment and to be useful to the environment, to measure what happens in the environment and to give information back. So this is mostly encoded in ZD, but it's extremely difficult to understand how to model ZD. So as a control engineer, I would design the feedback controller, not even the feed-forward controller, but then I need, for example, a sociologist to tell me that if I want to have this useful to a little child that wants to learn how to interact with a pet, then it should behave in a certain way. So a sociologist should tell me how ZD should be defined for this particular application. A medical doctor should tell me how ZD should be defined for this particular application. I want to help a person to start walking again, and this may have had an accident. Now, what happens is that I want to use a robot. You see, this is essentially a robot arm in such a way that I move the legs as long as this person is not able to move them. But then I have to be able to understand the maximum amount of force that you can use, and when there is a force applied by the patient, what you have to do. And actually, it's a very interesting experience because I experienced a similar device on myself. So I was able to test the controller that I've designed to myself. Fortunately, I mean, it was a good design because I'm still walking after that. Okay? So, but the type of, sometimes, the type of forces that you generate are too much. But it's a very good experience for a control engineer to try your own controller. All right, now, so the interaction with the environment is extremely important. And typically, you can understand this interaction as a set of disturbances acting on the system. And now the effect of disturbances has to be attenuated in this way. I mean, if you are flying on an airplane, there is a lot of wind, then you would like to have, a comfortable ride. So you should modify your system, the way you control the system, in order to reduce the effect of these disturbances on you. On the other hand, you may want to modify your goals because the environment is telling you that you have to modify the goals. So, there is always a two-way interaction. On one hand, you may want to attenuate the effect of disturbances on the way you would like your robot to behave. On the other hand, you would like to modify your goal in such a way that is compatible with the disturbance. Okay, so this is the application that I was discussing at the very beginning, the small application. So we have a project at Imperial that is actually dealing with this type of application. So this is used in a surgical procedure, and it's actually known that most of the recovery time after surgery is associated to the fact that actually they've opened you essentially, okay? So if we are able to perform surgery inside the body without actually opening the patient too much, but just make a so-called keyhole surgical procedure, then we will reduce trauma, post-operative intervention, and cost. I mean, this is extremely important these days. Now, the problem is that you should be able to navigate these objects in the body, and typically the access points are in your legs, where you can take an artery, for example, and you want to navigate all the way along this artery for half a meter, for example, to the coronary circle. Now, you would like to generate a steerable catheter which use electrothermal actuators. So what happens is that this is a little wire, we can think, that it will move as you apply currents because you hit this wire, and as you hit this wire, you generate deformation. And on top of this deformation is sort of memorized by this object. So if you want to navigate along a bend, you initially move in one direction, but then you stay in this direction because you have to move along this direction. So this is extremely important, and you can achieve this goal simply applying tiny little current along these wires and then controlling the temperature. I mean, the difference in temperature is actually not that big in order to achieve to achieve this type of trajectory, because you don't want to hurt the patient. And so this is actually implementable through a robot, and the so-called master-slave operation. So the surgeon will actually have something like a pen in his hand, and with this pen, he will control the robot, and the robot will essentially follow the path that is the surgeon is telling to the pen. This is important because if you think what you are doing while you're trying to insert a wire into a pipe, then this is the type of operation that you're trying to do. I mean, so you're trying sort of to steer your wire, and this is precisely what the surgeon is doing. Now, the surgeon cannot do this because the surgeon is not holding the wire in his hand, okay? But this type of command that is given by the surgeon is translated by the robot into movement of this probe and temperature shape for this catheter in such a way that you can navigate along bends. Okay, of course, this is a long way from being applied on real patient, but we're actually working on that. So we're trying to develop materials and techniques to perform this kind of loop. And you know, this is again a very interesting loop, because on one hand we have a position loop. We want to shape the motion of this probe, of this object inside a human being. On the other hand, we want to sense force. If you try to insert a wire, at some point you may feel that you're unable to push. You cannot push anymore because, for example, there is a very sharp bend. And so this type of information should be fed back to the operator. Okay? So the idea is that the surgeon or the operator will have this type of feedback all the time, and then will decide how to steer the wire inside the body. Now, typically, you don't do this blindly only with this type of object in your hand, but you try to be helped by imaging. So what happens as you go inside the body, you will have a few X-ray images in situation where you have problem navigating a bend, you have problem inserting the wire, and then with minimum X-ray imaging, you are able to understand how to negotiate the difficult situation. Okay, so what are the challenges for robot manipulators? So as I said, robot manipulators are the simplest possible object that we can think of. They are essentially mechanical systems with all sorts of possible different shapes, but they can be used for Terminator-type arms. They can be used for replacing limbs, for example, in a very simple way. And here you can have tactile sensor. I mean, if you think what the iPhone is doing or what all these parts are doing, there is a tactile feedback there. They sense when you touch. And this can be reversed, okay? So you can sense something with a small current where you touch something, okay? We'll come back to sensing in a minute. You may have patients eating. Again, this is a robot that will adjust the size of the tray on the basis of the force, on the basis of the position. So you may even have a camera which observe the way this person is behaving and adjust this tray and this table accordingly. And this is a sort of small exploratory robot, which is actually not really a walking robot. We'll go back to walking robot in a minute. But this is composed of manipulators that, you know, if they work in a cooperative way, they can actually move along the floor or a pipe and so on. And if you want, for example, to explore a long pipe, the pipe that is used to deliver gas from Russia to Europe, for example, you don't want to have anyone going there. You don't want to stop operation. So you want to insert 50 kilometers down the line an object like this one, and then you want this object to navigate for 50 kilometers and find the problem inside the pipe. Now, we were talking about tactile feedback. This is actually a very new thing and a very important thing, because you would like to be able to have a feeling that you touch the robot and the robot would like to have exactly the same feeling. And these are extremely important because you may have surgical telepresence, so the operator may be half the way around the globe and may move a robot, and then, you know, with a proper communication link, you may be able to do operation on some other place. You may be able to do interaction with hologram, and you may be able to do e-commerce. We all buy on the network these days. But for example, you want to buy, you know, a jacket, and you don't want to see only the color, but you want to touch it. Okay, you want to feel the fabric. So this is actually possible. I mean, it's pretty much something that, you know, you can sort of have a glove, and it looks like you are touching, but the thing is somewhere else. I mean, you don't even know where it is actually. Okay, and of course, you know, preliminary objects are these iPhone or smartphone types of things. A lot of games. I mean, if you think video gaming. When I was a boy, video gaming was a tiny little thing that you have in your hand. You were sitting alone on the sofa playing the game all day. Now, this day with the Xbox or the Wii, you are jumping all over the places with a lot of other people and so on. So this has changed significantly because you have this feedback. Okay, so because these robots are able to understand where you are, you have a sort of tactile feedback, and you can sort of use this type of interaction. So these are two examples of haptics interface. One is to drive a car. So you are driving this car, but you are not there. Okay, so this can be done. Of course, it won't be a good idea to do this in cities, but it may be a good idea if you want to move along a very unfriendly environment, for example. You may want to drive a car from far away, but actually rather than using very complicated commands, you may want to use something which is very simple, so the classical steering wheel, and you want to see what happens. And so you can do this in remote, but you want to have feeling. I mean, when you drive a car, you have some feelings, and this is extremely important to have. And also in this case, I mean, this seems to be type of machine which are very rough. I mean, they're essentially used to move ground from one place to the other. But what you want to do actually, you want to have a feeling whether this is too heavy, this is too light, and so on. So it is important that the operator, which is typically sitting somewhere here, has a feeling of the strength that is used by this huge machine, and has a feeling in his arm. Okay, so reduced by a factor of 1,000, but has a feeling in his arm. So tactile sensors are extremely important for this type of application. In this case, you may want to make sure that you don't break these big arms, for example, if you find a very heavy stone, or if you find a place where you cannot dig, you may want to have this type of thing. Okay, so what is the summary of this part of the talk? So, for robotics manipulator, unlike old robots where you just have mechanical pieces together and then some control loop, some motors, and some sensor, now we need to have high precision manufacturing. We have to have electronics, smart material, very good human-computer interactions, smart sensor control, and virtual reality. All these disciplines, and probably a lot more, signal processing, image processing, they have to come together if you want to have a mechanical system which is useful for a specific application, which is just not moving from one place to another. And then, of course, you have all type of beneficiaries. I mean, in rehabilitation, I stress this quite a lot. Toys, e-commerce, construction industries, monitoring, mobile devices. And even if toys is not as important as medical robotics, I mean, if you think of the type of revenue that you make out of toys, I mean, then all of a sudden it becomes extremely, extremely important. Okay, now the second part is mobile robots. So a very interesting type of mobile robot is this American fire truck. Why it is very interesting? Because this is so big that actually you can steer the wheels here and you can steer the wheels here. Okay, so this is very good because if you want to go around streets with such a huge vehicle, it's extremely useful to be able to steer these wheels. So in practice is to help you steer along the road. On the other hand, driving something which has steerable wheels, fixed wheel, and steerable wheels is extremely difficult. Okay, so if you want to, and the type of motion that you have for this system is actually very unnatural. So if we could please play this video, so you'll see that it actually goes on the way back in a very unnatural way. It's not the way you would go with a lorry where you cannot steer this, but it's very unnatural. And this means that typically there is an operator driving here and an operator driving there, and they have to communicate to each other, and they have to be very smart and very experienced in order to park this type of object. On the other hand, you can park this automatically. You can design a controller that does this automatically, which makes use of a differential model of this system, typically a kinematic model because this is a geometrical problem, and from this differential model you find the controller. Now, how do you describe this? Well, the mechanical part is pretty much the same, but the type of constraints that you have for mobile robots are completely different, because for mobile robots you have so-called velocity non-autonomic constraints, which means you're not constrained in the way you move, you're not constrained in the type of configuration that you can reach, but you are constrained in the way you move. When you want to park the car, we all know very well that you cannot just park it sideways. Okay? There is a constraint, which is a velocity constraint. I mean, with your car, you could go wherever you want, but you cannot go wherever you want with every possible trajectory. There are feasible trajectories which are satisfying these constraints, and there are trajectories which are not feasible. Typically, the type of constraint is that the velocity orthogonal to the wheels should be identically equal to 0. But since you steer the wheels, this is a constraint that will change on the configuration as you change the configuration of the system. So if we have a look at a very simple mobile robots, and then you want to park this robot from all over this initial condition to this final condition, well, it's very simple to devise trajectories that will go and will sort of move the robot from one position to another position. However, we see that some of these trajectories are pretty natural. I mean, if I want to go from here to there, it's quite natural to go forward and up. If I want to go from here to there, this is even simpler. I mean, it's essentially just going around an arc of circle. If I want to go from this position to that position, again, I could go there. But why not go in reverse? You see that there is a symmetry in this type of picture. And similarly for the position up there. This means that, let alone strange trajectories, but even natural trajectories for motion planning for mobile robots are by all means not unique. And this is the simplest possible mobile robots. Why this robot has to move in this way? Because we have a constraint on the velocity orthogonal to the wheels. So you cannot slide in this way. You can only move in such a way that you have a small rotation, and then this constraint here will be directed in this way, and so on. So essentially, you have to move in an orthogonal way to the constraint. In this case, the constraints are very simple because you have a pair of wheels. But if you have 2 pairs of wheels, 3 pairs of wheels, then the constraints get more and more involved, and the type of motion that you get becomes very difficult. So motion planning for mobile robot is not a trivial task because you may not have unique solution to your natural motion planning problem, and because you have the constraint acting on the system. Now, of course, how is motion achieved? So I've already mentioned that the type of constraint that you have is the no-slip constraint. So you cannot move sideways. A wheel, even a wheel with a tire, but an ideal wheel, will not be able to move sideways. Okay? So you are not able to slip, you can roll only. Now, if you have a robot, like a walking robot that is running, what happens is that you hit the ground, you jump, and as you are in mid-air, you have conservation of the angular momentum. Okay, so you can do a lot of things. You can move, the legs and so on, but the total angular momentum vector, the norm of this vector is going to be conserved. So you have to take this into account when you design an algorithm for a walking robot. If you have a walking robot, so you don't jump, you always have feet on your ground, what happens is that here you have a constraint. This feet has to be on the ground. And on the other hand, this is completely free. So you see that you have a kind of manipulator. Okay, so this is a robot with a lot of link, where you have a constraint on the acceleration on this feet. But then as you do a step, everything changes, because the constraint now is on the other feet and so on. So you have what is called under actuation, because there's something that you cannot move. There's something that has to be on the ground, and so you cannot move. So this is a very simple example of a mobile robot. And could you please play this video? Yeah, okay. No? Okay. Sorry. Click again, click, yeah, okay. All right, so this is a robot a walking robot that has been developed at University of Michigan. And actually this robot has won, you can reduce you can take the volume off. So this robot has won the prize for the fastest walking robot that has been designed. So this robot is very heavy on the torso and very light on the leg, because we probably all know from experience that you can walk very fast if you have a lot of weight. For example, if you have a rucksack, but it's very difficult to walk very fast if you have very heavy legs. I mean, if you put skiing boots on your on your feet and you try to run, then you have really a problem. Okay, so it is important to have this type of configuration if you have to have a walking robot. Now, the kind of support that you have for the robot, the lateral support, was simply because you don't want to be interested in what is the sort of lateral motion of the robot, but only on this motion. Now, the other important thing that you want to do is obstacle avoidance and path planning, because it's all very well to say that I have a starting position and the final position, but all of a sudden I have some obstacle. And this obstacle may be time varying. You know, someone may be shifting a chair, maybe moving something. So your robot will sort of try to go from here to there. If it's a robot that has a few sensors, will actually don't hit the obstacle, which is good, but will not be able to know what to do. So the next step is for your robot to be able to do something like this. And so actually this is not, you know, it's not made up. Actually, we developed an algorithm to achieve this goal. So what happened to the robot? The robot, in a very simple way, will try to make sure that at each time instant it will minimize the distance between his actual position and the goal. Okay, so the natural trajectory is a straight line, right? But then this notion of distance has to be changed as you move in the presence of an obstacle, because the obstacle will generate, for example, if you have some sensor, a signal that you have to use in order to modify the notion of distance. So if you are close to these two obstacles and close to the robot, from a physical point of view, you're actually very far away from this robot because you have the effect of the proximity to the obstacles. So your robot should be able to get closer to the final goal, which is to navigate away from the obstacle, and it will do something like this. And you can do this in a much more sophisticated way as you get more and more complex tasks. The robot will initially try to go along this straight line. Of course, there will be some noise because of the sensing, and then, you know, it will be tricked into this position, but then it will figure out that there is no way out and will come back. All this is autonomous. You only tell the robot that you want to go from here to there, and you have three sensors, one in front of you, one to the left, one to the right, that are telling you whether you are close to an obstacle. You have only three sensors because this robot only goes forward, it doesn't go back. And then you have a slightly more sophisticated task, and a slightly more sophisticated task, and finally you have this type of task. Okay? But now you would think that, you know, okay, so this is an academic example, and of course you can devise a controller that achieves this goal. Keep in mind that we have not changed the controller from this, well, yes, for this situation to this situation, we have modified the controller. We have defined a new notion of distance, which takes into account the effect of the environment on the distance. But from here to there, we have not modified anything. It's always the same robot. It's always the same type of controller. So the robot is able to understand that there is a dead end to come all the way back and achieve the goal. Okay, actually there is so-called micro mouse competitions, which are for students your age or even younger. So the problem is to devise mobile robots, mice, to compete against each other to solve a 16 by 16 maze in the shortest time. You have no information on the maze. You only know that it's 16 by 16, and you can use whatever you want. So if we can play these two videos together, this one and this one. So you see, okay, forget the music. And okay, so this, we play the other as well. Sorry, can you play this as well? Sorry. Okay, so this actually is trying to follow all walls. Okay, this is actually a mouse, an old computer mouse, as you can see. So it's a real micro mouse, if you can think of it. And the behavior is pretty much the same. I would say that in both cases we have very poor design. Okay, sorry, stop and play this one now. Okay. All right, so these are actual, much more sophisticated mouse. Unfortunately, the quality of the video is not that good, and you cannot even see this micro mouse. And it reaches the goal in 11 seconds. Okay, and you know, if we are patient, then let's see. This one actually is not that good. All right, so you see that it's going everywhere. Okay, sort of a complete search. It's a very fast mouse, but not very smart. Okay, so you see that it's going inside all of them because the center is somewhere there. You see, that's not good. Try, and then it will find the right opening and reach the goal after that. You see, so it's essentially tried them all. It's not very smart, it's very quick. Okay, so now it's gonna make it. And you see that this mouse is very good on diagonals, it's not very good on straights. Yeah, so it's back where it was before, but now it gets a bit smarter. He's learned a bit of lesson. So we cannot really see it. Where is it? Yeah, here it is. Now we'll navigate inside. It has to take this, yeah? All right, now it's good. Okay. Now the next one will probably take 5 seconds, okay, or probably 8 seconds. So it is really amazing. So the difference is that if you start in this direction rather than the other direction, yeah, you are in a better position. Is that? Okay, so yes, absolutely no information on the maze. Okay, you can stop and go back to the slide. Oh, sorry, no. Next slide. Yeah. No. Okay. Right, now, mobile robots. So, we have seen a game, this micro mouse competition, but actually they can be useful in a lot of other applications. So, one robot that I personally designed with the help of a lot of colleagues is a robot for a data center. Now, in Rome, there are several data centers, but the one that is taking care of the Italian railway system, and you shouldn't blame me if the railway system is not efficient in Italy, is composed of 12 rooms. Each room contains approximately 6,000 servers, and these 6,000 servers, the room is much bigger, each room is much bigger than this room, but they are in corridors, okay, and this, you have 6 servers, so you have 1,000 piles of servers for each of the room. And then what happens is that during summer it gets very hot, and you want to use air conditioning in a very good way. Now, to use air conditioning in a very good way, you need to measure temperature of each one of the servers. Now, the dumb approach to this is to have 6,000 sensors to measure the temperature throughout. But actually you think that, you don't really need the temperature every couple of seconds for each server, but you just need a robot which will go around and will measure all the temperatures. Now, you really have large temperature variation in this type of room, and if you use air conditioning in a very good way, you can save hundreds of thousands of euros a year. So this is a very worthwhile application. Now, let me show you the robot that we have developed. So if you can click this video, please. Okay, so this is completely built in the university. So it's a very small mobile robot, and the black path is the black path that you have to follow. The reason why you want to follow a path, you could use a GPS. Why you don't want to use GPS? Because you will have a lot of interference. You don't want to have Bluetooth, you don't want to have anything like this because you have all these servers which are running there. Now there is this big object there where you have all the temperature sensors. So you reach a station, you stay there, you measure temperature, and you go on. You essentially move along a corridor which is in the region of 3 to 4 kilometers inside a small room in 1 hour. And this is good enough for the type of application that you want. Now you have to keep in mind that for this application it doesn't make sense to have a very fast robot, because a very good temperature sensor will actually measure temperatures in 10 seconds. Because you have the temperature of the air, you have to take care of the fact that you reach the steady state and so on. So it's important to have very good temperature sensor, but then you have to be slow, because if you move, the temperature sensor will not reach steady state, and then what you measure doesn't make sense anymore. Okay, so let's go new slides, please. Okay. Now, another important problem is in robot control is to understand where you are. Okay, so you have a robot moving in an environment, and typically you have information from a camera. You can see your robot, but you want to understand how far away is this robot. So this is called range identification problem, where you have 3D information. The robot is somewhere in space, but you have 2D. You want to reconstruct 3D information from 2D information. Now, this can be done only if there is a change in something in the robot as you move. For example, there is a disk here, and the area of this disk will change as the robot moves. So if the robot gets closer and closer, this area, seen from the camera, will actually get larger and larger. So if you run this video, please, you can have, this idea that the robot is moving forward very slow, and then it bends a bit to your left, but then the area will increase and it goes forward. Now we want to have information on the measured area, and you see that this blue line is actually a way to measure the area. We'll come back to measurement of areas in this way. So it's important to understand that this is a feature of the robot that changes in a 3D way. It's going to give you information on the 3D motion of the robot. So the distance, the blue one is the actual distance from the camera. The red one is the estimated distance with the noise, which is associated with the noise by which you measure this area. And this is the actual area. You see that it gets larger as the robot approaches. And then you have the actual one, and you have the estimated area. Okay, now what are the challenges in mobile robots? Okay, so you want to build mobile robot for all sorts of applications. So these are rescue or robots, both of them. Then a mobile robot is pretty much like a robot in space, because while for a mobile robot you have velocity constraint, also here you have velocity constraint and conservation of angular momentum and conservation of, lots of type of conservation. Then you would like to have domestic robots. You want to close a drawer, you want to shift a table, you want to shift a box. Then you would like your robot to help you with this task. Again, this is very useful if you have elderly person at home and they're not able to perform very simple tasks, for example, to move a table or to shift something, and so the robot may help you. And now there is an international goal, which is to have a robot which is able to attend a national conference on artificial intelligence. So the robot should go there, should register. If you go on the web, there is a long list of specifications that this robot should be able to achieve. And one of them is to attend lectures and ask questions. Now, this is probably a bit far-fetched, but is the goal that we want to achieve. So, as a summary for mobile robots, we have expert system, artificial intelligence, communication control, smart sensor, and so on, an interplay between all these disciplines, and the beneficiaries are again medical robotics, exploration, monitoring, rescue operation, manufacturing industry, smart buildings. You want to measure temperature and the environment. Okay, now the next step is flying object, autonomous vehicle. So suppose that I want to design an object, a controller that works for this type of small model, which is an XRA 140. It's not even able to take off, so essentially you have to launch this aircraft and then it will fly, or for the Eclipse type of aircraft that is developed by the British Aerospace. So these can be even used in military action or in rescue operation. Now, there are a couple of challenges, so if you can play both the videos at the same time, please. So you want to be able to navigate across an obstacle without knowledge of specific of the obstacle, but at some point you would like to have a change in your attitude. So you don't want to have any overshoot. Now the other objective that you want to achieve, can you play this left video, please? Yeah. Okay, so you want to take off with the same controller. Then you are at some altitude. You have a bend, 180-degree roll. Of course, you don't want to fly on this plane. And then it will resume normal flight and will have a very sharp figure-8 type of trajectory. So you go back where you took off, and then you have this type of behavior. All this has to be achieved with a unique controller. Okay, so you don't want to have game scheduling, you want to have several controllers, but you want to have a unique controller. In addition, you would like to have a unique controller for this object, for the other object, and you would like to have a unique controller for all type of aircraft. How is this possible? Okay, let's try to go back to the specifics of the problem. So if we have a rigid body moving in space, classical mechanics are telling us that we can model this with differential equation. We have the Euler equation for angular velocities. We have the attitude, which describes the position of this body, the attitude of the body, the rotations of the body with respect to a reference frame. So A is an orthogonal matrix. We have variation of the kinetic energy of translations, and then we have the actual position in space. As you see, the actual position in space is a function of the attitude and of the velocities of the object. And then we have a geometric path. So a line or a circle or whatever, which is specified in terms of a constraint on the x, y, and z coordinates, which are the 3 coordinates of Q. So our goal is to make sure that we are on the path. Okay, so you have a flight path and you want to be on that path. So this is pretty much an idealized object. but actually we want to be able to use this approach for all these types of objects. And now, what is the important difference here? So what is the object-specific part of this particular type of application that shows up in the equation? Now you see that is the actuation, the way you move, you make this object fly. So this is a classical actuation, for example. This is non-classical actuation because you have all these rotors. And this is, again, you have 4 rotors and then 1 over there. So you want to be able to design something which is useful for all this type of aircraft. And the difference is so the challenge is really that you don't want to have any knowledge on the so-called aerodynamic parameters, aerodynamic forces and aerodynamic momenta, which are the TE and the FE. So the way this object interacts with the environment. So what you do, you pick one of these objects, and then you design a UAV-dependent feedback. Okay, so for each one of them, you have a specific feedback. This is not good enough. So you want to be able to learn which one of these particular flying objects you are taking into consideration. You have what we call the universal learning mechanism, and now you can close the loop. You learn which type of vehicle you have, and you use now an independent UAV-independent feedback. So this feedback, together with the learning mechanism, will work for any one of the vehicles over there. And then, in the particular example, the UAV-independent feedback and the learning mechanism will be split in an airspeed control, which are essentially telling the forward speed of the object, and the attitude control, the way this object rotates in space, and then you have a path tracker, which achieves the final goal. So let's see a couple of challenges for this. This is actually a very tricky operation. You have a carrier in high seas, and you would like your helicopter to land on the carrier. In high sea, you will see that there is an oscillation here. Okay, so the deck of the ship will go up and down. So before going down, you have to synchronize your helicopter with the motion of the deck. And you have no information on the waves. Actually, you can have some information on the waves, but typically you don't have lots of information. So you will have to synchronize these, and then these will go down. Now let's see another type of application. So if you can click on this video. So we have a type of path following application where there is a car, yes, that you want to follow with this helicopter. You have no knowledge of the car. Essentially, you are following a red mark, okay? So this helicopter has to follow the red mark without knowing what the mark is doing and with an eye on the environment, okay? So it's extremely difficult to navigate in a city, and you want to follow this car. I hope the quality is reasonably good, right? And so you see that sometimes the helicopter does some very strange motions because there is an abrupt motion of the target, and you can pose this as a control problem that the shadow of the helicopter should be on top of the car. Okay, so this is your error. Okay, there should be one on top of the other, and then you need to follow. This. Okay, so we can stop the video. I mean, it's a bit longer, but this is essentially giving you the type of information that you want. All right, thank you. Okay, now what are the challenges? Well, we've seen some of the challenges already. For example, the construction of one of these energy generators, micro, helicopters or micro flying objects. This is actually an idea that has been developed from the military applications, because soldiers in Afghanistan, for example, I mean, this is the Ministry of Defense in the UK, they would like to know not really where the forces are deployed and so on, but they're much more concerned who is outside that door, okay, because this is much more dangerous. So if they could have a couple of these little flying objects and, like flies and throw them, and that these objects see what is around the corner or outside the door, is going to be extremely useful. And so it is possible to design this tiny little object. This is a paper clip with a tiny camera to achieve these goals. And now we've discussed about actuation. Okay, so this is a scrum jet. It's a jet that is supposed to go at Mach 10, and the motors are being developed. Now, talking about actuation, I say that most of these robots, most of these vehicles are using classical actuation. So you use rudder, ailerons, elevators, and so on. But actually, you could use shape memory alloy in order to modify the shape of the wings to reduce turbulence. And something that has been used, and I've done some work on this, is to use small jets of air in order to reduce turbulence on the wings. Okay, so it has actually been shown by Airbus that you can reduce the amount of drag, and so the fuel consumption significantly if you use these little jet of air, because they are able to destroy turbulent flows along the wings. So UAVs can be require computational fluid dynamics, aerodynamics, visual feedback control planning, micro electromechanical system. You have to have knowledge of chemistry, structure, advanced material, and so on. And you can have beneficiaries in wind power, commercial aviation, the defense sector, monitoring, supervision, video games, toys, and so on. So all these type of defense application, they will eventually filter down all the way to toys. Okay. All right, now we go underwater. So now we have a problem, and we all know what is a submarine, and the submarine is controlled in a very simple way. We want to have a different type of submarine. We want to have a submarine that will go all the way across the Atlantic, for example, with minimum interaction with the environment. Minimum interaction because we want to reduce pollution, we want to reduce any action on this. And so we want even to be able to have a vehicle that doesn't have any moving surface outside. You don't want to have elevators, you want to have rudders, ailerons, or moving fins. So the only thing that you can move are inside. So you can move a mass inside, which means you can move the position of the center of mass of this object, and you can pump water in and pump water out. Now, why you want to do this? I mean, suppose that this object is naturally buoyant, so it's somewhere in the water in this position, and then you move the mass forward, then it will tilt, and it will go down, right? Now you have to make it come up. Now the only way that you have to have this object to come again up is to reduce the weight. So what you do, you reduce the weight, you push water out, and then you move the mass back, which means you tilt it in this way and then it will go up. This is actually a very tricky control problem. It's a very slow process, but it's very sensible because it's very sensitive, sorry. You need to make sure that as you move this in one of these directions, then this is done in a very gradual way, because otherwise the object will just go vertical and either sink or float immediately. Okay, so in terms of mathematics, the difference between underwater vehicles and classical vehicles are tiny and depends on the type of actuation. Now, as a matter of fact, they are flying in water, so if you have classical actuation, they're like airplanes. Okay, so in underwater vehicle, you have Kirchhoff law, unlike Kirchhoff equation, unlike Euler equation. The only difference is that you have the action of the water, which is a fluid pretty much like air, but it's much stronger than air. So the action of water is much more significant. If you have internal actuation, then you have something which is closer to a mobile robot. Okay, so this object is like an aircraft, so to speak. This object is like a mobile robot. And so you can use the same ideas in order to control both of them. If you have underwater manipulators, then these are similar to standard manipulators or to space manipulators, depending whether they are fixed on a very stable platform or whether they are floating. So a space robot and the manipulator underwater, which is not fixed anywhere, they are essentially the same. Okay, so the type of problem that you want to solve, you would like to go up on the surface, transmit whatever you want to transmit, receive commands, and then you want to dive, and then you want to come up after some time. And then you want to save energy. You don't want to do anything for most of this type of your trajectory. Here, you decide to go up, then you switch something, you go up, you don't do anything, you transmit, and so on. So the type of scale that you can achieve is 5 kilometers for this type of sawtooth behavior. You can go down 1,000 meters, and then it will take 10 hours. Extremely slow, almost no power consumption. So if you can please play this video. So you can see one such a thing. So it's going down, and then there's no external motions. So you change the mass inside, and then it will come back out. Just a second. So here is the tilting point. The mass will go all the way backwards. You push water out, and it will come out. The quality of the the quality is not that well, but I can send you the video. Okay, back to the slide, please. Okay, so what are the challenges for underactuated robots? Well, is to define objects which can blend with the environment. For example, this is a type of underactuated robot that has to be used to learn the way underwater life is organized. So you want to make pretty much similar to something that a fish would be able to sort of recognize as a known object. And then you may want explorations. And, the whole idea is that these objects are supposed to go up and down in the water with minimal interaction with the environment, minimum energy consumption, and they should be able to reach a position where they use energy to change their path, they transmit whatever information, they receive whatever information, and then they go the way down. So you can explore a large area without actually a lot of energy, and this is completely unprecedented. I mean, classical actuation will be far too expensive for this type of operation. So for underwater robots, again, we have communication. Remote operation is extremely important to tell the robot what to do now, and then you wait 10 hours next time that you see it. So the whole notion of feedback is actually very strange. I mean, we all think that feedback is something online. There we have a sampling time of 10 hours. You tell what to do, and then after 10 hours, you update the position, and you take decision. I mean, if you take a much larger scale of this type of problem, if you have a space probe or something that is sent to Mars, for example, this will turn on every week, for example. So at a 1 week distance, you will measure where it is, it will send back data, you will give new command, and then it will be essentially a stone without any information for another week. Okay, so control has a sampling time of 1 week, and this is a very difficult problem. Now you may have application in exploration, monitoring, rescue operation, on industry, ecology, environment, and so on. All right, now dynamic set. So suppose that now we want to understand collective behavior, because before shaping collective behavior with this notion of consensus that we're going to see at the end, we would like to understand how a group of objects of different types will behave. And you see that when I specify a group of objects, well, we all agree that this is a cloud of dust. I mean, it's composed of tiny little particles, but actually we are not interested in the behavior of the particles. We're interested in the cloud. The volcanic cloud that made a mess last year for all air traffic in Europe is something that you are not interested in the particular tiny little bit of the cloud, but you're interested in the overall behavior. Here is a flock of geese. You want to understand what is their behavior. You want to see what they collectively do, not what each simple goose is doing. It doesn't matter that this is the leader and these are the followers, because they may move as you go along, but the shape will be always the same. Okay, so this is important. How do we formalize this? Well, we have a set of what we call dynamic objects. So these are moving in a plane for simplicity. And then we want to find the collective dynamic description of the set, not of the object. And then we want to be able to forecast the future behavior of the set, not of the object. Now we may make some technical assumptions. But what is important is that the object can appear and disappear. Okay, so if you have a flock of geese, one goose can decide to stop at some point. So you cannot really track each single one. You have to track the shape. And then you want to have a notion of correlation. Objects which are close, in whatever sense of closeness we can think of, have to be correlated in some way. They have to belong to the same set. So this can be done in a very simple way. You can construct, for example, Gaussian functions. This is not really a probability density function because it doesn't have all the property of a probability density. But you can think of it like probability that an object is in a particular area, a particular region of the space. For each one of the objects, you add all of them together, and then you have a clustering function. And then you slice this function. You see? If I slice this function, here you have a set, and this set is telling me that 3 objects are closed, and this object is somewhat isolated. This may change with time. Okay, so the object can move, and this one can go together with this, or one of these can go far away. So we want to model this situation. So the parameterization is done in terms of level line of this clustering function. So if you have a flock of geese, then they do clustering at a very fine level. Each one is an individual object, or you can do clustering at this level. So you have a formation, a typical V formation, and then you have 3 singletons that are essentially doing something different. They may change as time goes by, but this is the way this is behaving at this particular time. Now, what is the advantage of this type of description? The advantage of this description is that you can use the theory of Hamiltonian system. So this is an Hamiltonian system to describe trajectories, okay? Because Hamiltonian systems are conservative systems, trajectory will evolve on level line of the energy functions, and exactly if you initialize your object on a level line, on your trajectory, you're always going to stay there. Then, on top of this, you can compute geometric moments. So you can compute the area, you can compute the center of mass, you can compute the sort of ellipsoid approximating this set. And then you can solve the cluster validation problem, which means which object belongs to this cluster, and then you can define a dynamical set which describes the motion of the sets. Okay, now we've done an application to clouds. That's what I was discussing at the very beginning. So these are infrared picture of Hurricane Ike. Hurricane Ike is somewhere here, and you want to forecast where it is going to go. Okay, so you can take this picture from the National Oceanic and Atmospheric Administration website, and they are at every half an hour. These are infrared pictures. So this is one such picture. So suppose that I take pictures for 6 hours, 12 pictures, and then I want to forecast other 12 hours. So first of all, I need to identify the clouds. And the one that I'm interested in, which is Hurricane Ike, is this one, which is entering this image right now. But then you have a lot of other clouds. Okay? So if you can play this video now, so you will see the way Hurricane Ike is actually moving. Okay? And what is important is that you have here a dynamical system. By all effect, it's a dynamical system, but it's not the classical dynamical system that we all know. What is the state space of this dynamical system? It's the space of sets. It's a very strange state space. But on top of this, if we have a dynamical system, a differential equation, we all know what is the notion of past and what is the notion of future. In this particular example, is extreme. Well, in general, for sets, it's very difficult to know what is the past and what is the future. What is the past of this cloud? Because this cloud may have been composed of several clouds. Okay, so the past is very strange. This cloud may disappear. It doesn't have any future. Okay, so the notion of time is extremely difficult to understand. Now, the problem that we had before is to track the motion of Hurricane Ike. So we measure data over 6 hours, 12 images, and then we do forecast, and you can do this online. And now the red line is the motion of the center of mass of Hurricane Ike, and the green line is the estimated motion of the center of mass. And you see that we are reasonably accurate. And now you see also that the behavior is very, very strange, because it's affected by pressure, by wind, by a lot of other things, interaction with the environment. But what is important, you want to understand where the hurricane is gonna go to land. Okay, in this position, in this position, in this position, and the center of mass is the important bit of the hurricane that you want to understand. Okay, what are the challenges here? So, you want to track bushfires, for example. Sorry, just a second. You want to track the shape of a flame in an incinerator process, because you know that you are dealing with waste if you burn them in a special way, and in the flame have a special shape. You want to be able to recognize objects at seas, for example, from a very strange, for a very possibly non-clear image. And now this is a very interesting application. The video is not very good. This is a set of mosquitoes. Now mosquitoes, malaria mosquitoes, which are extremely important to control, they move in a very special way. So the idea is that they generate a cloud, and you would like to cluster the cloud in order to understand what is their natural behavior and to modify this behavior in such a way that they don't reproduce. Now, unfortunately, the video is not very easy to see, but if you play it again, please. Can you play this video here? So, well, the male mosquitoes are all flying in the center, and the female mosquitoes are somewhere on the side. Then when they decide to reproduce, the female mosquito will jump inside, but they will jump only if the male have a special shape. Okay, so if the male have a special shape, a nice shape, then the female will jump into this circle. So this means that if we are able to recognize the good shapes and the bad shapes, we are able to prevent malaria mosquitoes from replicating, which means we are controlling mosquitoes, not malaria, which is a much better way of approaching the malaria problem. Okay, now the type of tools and technology, we have signal processing, databases, expert systems, smart sensor, and dynamical system, but very strange dynamical system, like systems on sets. And then beneficiaries may be the police, coast guard, firefighter, waste to energy processes, typical processes, malaria control, weather forecast. Okay, so this is the last part of this presentation. Now we know how to understand the motion of a group of objects, and now we want to make sure that they move all in order to achieve a goal. Now we define a notion of consensus. Consensus means they all agree. Actually, the notion of consensus is very weird. I mean, inside this room, if we decide to go somewhere tonight, it's impossible that we all agree. Okay? I don't think we'll ever have a group of people who are agreeing. So you have to approach the problem from the other end. You have to minimize disagreement. Okay? So this is extremely important in the notion of consensus. You don't reach consensus, you minimize disagreement. Now, typical case of consensus are the GPS constellation of satellites. Actually, you don't care what they do as long as they're shaping that way, because they can move in all possible shapes, but they have to be at that distance. This is natural consensus. This is consensus on the road. This is called platooning. You see that actually this is like a big car. Okay, so this one is driving and they're all at the same distance. Okay, if you brake, they will brake. This is a very difficult problem because you have a propagation delay. But rather than the visual delay, here you have communications. Okay, so the car will tell the other car what to do. It's not the driver that will see the other car. And this is an example of bad consensus. Here is a wind farm, and you see that the wake turbulence generated by the turbine is such that only the first one are producing energies and all the others are producing nothing. Okay, because they only have a turbulent fluid. Okay, so what we want, we have a group of objects, of agents, and they have to achieve a collective goal. In this particular case, you are maximizing energy generation for the front row, and you are setting to zero energy generation of the other rows. This is actually not a very good strategy. So you have communication pattern, a communication topology, an actuation structure, a decision strategy, and you want to achieve a common goal. So suppose that you define this object. It's important to understand that there is no leader, no reference. In the example that we had before, if we want to decide where to go out tonight, there is no leader. Okay, everyone has his own opinion, and we try to minimize disagreement. But there is no particular leader, there is no particular reference, there is no particular place where we want to go, but collectively we want to take a decision. Now, relative sensing is fundamental source of communication. You can imagine that if we decide to take a decision on what to do in the evening in the following way, I will tell her what I want to do, she will tell him, and then all the way, we may reach a consensus. If we decide on a different strategy, for example, I start from the other side, we may reach a different consensus. If we decide to talk all together, we may reach a different consensus. So relative sensing, relative communication is important because it will tell you what you achieve. So this is the example of the telescope I was mentioning at the very beginning. And so this is no consensus, consensus. Okay, so you are watching one star or two stars. Well, if you have no control, this is what you have. If you achieve consensus, then you have a much sharper image. Okay, so this is a very typical example how consensus can make a difference. Okay, all these objects are achieving a common goal. Okay, and it doesn't matter whether this telescope is 1 micron here, 1 micron below, and so on, but all the mirrors should be in a very good position. So the goal is expressed in terms of relative distance. Disagreement between me and the next person down the line for the decision process has to be minimized, but this doesn't mean, we have a relative distance, not an absolute distance. So suppose that we have vehicles, and then here we have directions. They are moving each one in one direction, and we want to achieve consensus. And the constraint is that each one can talk only to the neighboring one. Okay? Now, what happens is that you have what is called the centralized consensus. Eventually, you will reach a consensus. You may go this way, you may go this way, you may go this way. This is not important, but you all agree. So disagreement is minimized in this particular example. Now, the type of communication pattern that you have is called gossiping because each one is talking randomly to a neighbor. Okay, so you don't have any particular structure. Okay, now, another application is ocean sampling network. You have a group of objects and you want to have a specific trajectory for the group, but not for the simple object. We have seen that these objects have very strange trajectories. They have to go down, and up. So if you go back and look at the trajectories of the simple object, these are actually not very useful. You see that the black lines are the trajectories of the object, but overall this formation will actually doing a good trajectory. Now, consensus, collective behavior. So you have consensus, which is agreement in space, synchronization, which is agreement in time, and then rendezvous, which is agreement in space and time. You want to meet someone at a specific place at a specific time. It doesn't matter whether you are both in the same place at different times. It's completely irrelevant. Or you are in different place at the same time. Okay? So these are three types of collective behavior. Can you play the first video, please? So this is a very short video, and then you have these agents. They're flying all over the places, and then there is some consensus. You actually don't know where they're flying. This is not important, but they all fly together. It's a formation. It's like a flock of birds. You can stop this video. Next one. This is a more interesting video. You have these mobile robots, and they have to achieve a common goal. So they have to move this object. And you see that they reach a formation, a circle, but there is no leader. There is not anyone which is pushing and anyone which is pulling, anyone that is leading this formation and so on. You see, they will change. Right, so collectively the center of mass of this formation should be consistent with the center of mass of the object and should move in a special way. What each single element is doing is totally irrelevant. It's not part of the problem. Okay, so they can keep on moving like this, and you know, some of these motions are very strange. You could ask yourself, why didn't you just go all the way up? Because this is not what is specified. What is specified is that they should move all together to achieve this goal. A much higher level type of goals. Not for each one you have to do this, this, and that. Okay? Okay, so applications are type of, I would say, computer controlled traffic. This is a long way to be achieved. Then control of oil spills or control, these are so-called red plankton. So you want to sample the ocean in order to understand the way some ecosystem behaves. Now, another very interesting application of consensus of cooperative system are the so-called tensegrity structures. So this is a structure that is composed of cable and strut. Strut are pieces of metal, typically, that you cannot bend, whereas the cable, you can sort of extend the cable. So these are fixed length, fixed shape, and these are variable length. And then you would like to have a continuous deformation from one position to another position. So you can reshape this with the constraints on the strut, but you don't have any constraint on the angles from this position to this position. And that way you can build very huge objects. I mean, if you see all these type of objects that sometimes are built for exhibition, these are built precisely in this way. Okay? Okay, so as a summary, consensus control, you have communication algorithm, typically in gossiping, graph theory, topology, and material. And you can have application in the environment, biology, oceanography, geodesic domes, which is the one application of the tensegrity structure, monitoring, supervision, fire monitoring, weather forecast, and so on. Okay, now robotics, in this much wider sense than what used to be understood at the very beginning, has a very special social impact. And this is actually what is defined by the IEEE to be the social impact of robotics. So I don't need to read all this line. And this is a set of applications that it is believed, in which it is believed robots can make a difference. All right, so this is everything from me, and thank you very much for your attention.